Thank you. That's a sufficiently embarrassing introduction. I'm really happy to be here today. I really enjoy doing this kind of thing. I'm delighted to share what my field is with new audiences. And so what I propose to do today is sort of a very informal show and tell session. And so I think I'd like to start by getting to know you a little bit. So I'd like to start, I think, with maybe just hold up fingers. I want everyone to hold up fingers. So I want to know how much you know about material science and engineering, okay? So one finger means that you don't think you've ever heard of that before, like today, or before enrolling for this conference. And 5 means you just published, a book on material science and engineering. So anywhere in between, 1 to 5, go. All right. Wow, we have like remarkable consensus here at about 2.2. Okay. Okay, good. Good. Well, so how about this? Does anyone have a definition of what material science and engineering is? It's worth a shiny dime. I'll give you a shiny dime to anyone who will volunteer a definition of material science and engineering. Don't be shy. Shiny dime, please.
Maybe the development and study of new materials in application for general engineering and bioengineering.
Good. That was very good. Any other ones? How about back here? Yep.
I would say that what I've heard is that there's a ceramics and a polymer side to material side. So that when you're talking, but you were talking about metals, and I'm not sure where that fits.
Okay, so we got metals, ceramics, polymers. We got applications. Good. What else we got?
Graphene as well.
Graphene.
Yeah.
Yep. Very special type of material. So we've got metals, ceramics, polymers, graphene.
There's a scientist where he works on like coatings for airplane turbines.
Yep. Those are usually ceramic on metal, in fact. Yeah, so good. What else?
My sense is that from the people I run into, that it kind of brings in people who may be from physics, this is more in terms of how it is as a discipline, physics, chemistry, various engineering fields,
Yep.
and subfields of all of those things.
You guys are good at this. Okay, so one of the points I was trying to make here is that this is a field, material science and engineering. It's not a field that everybody necessarily knows what it is, right? You don't take a class on material science and engineering in high school. You know what physics is, and you know what chemistry is, and you know what biology is. You might even know what mechanical engineering is. Every kid builds a robot these days, right? But very few people sort of have a clean, crisp definition of what material science and engineering is. However, if I aggregate all your responses together, I'm basically going to spit all that right back at you because you have it right. The way I bill my department at MIT is that we are engineers, we are builders, we are designers, and what we build is solid matter. So my tagline is that we are the architects of solid matter. And what I mean by that, when the clicker starts to work. All right. Yeah, it's on. Story of my life. All right. It's not going to work on here either, is it? So the computer is frozen. All right. All right, so material science and engineering is essentially everything that you just told me is exactly true. What we study in material science and engineering is how to build solid matter. So here's the way I like to think about it. You all know what a mechanical engineer is, right? And if you think about what a mechanical engineer does, they take components like gears, sprockets, bolts, and they put those things together in novel ways and they make engineering products, right? They make engines and they make mechanical devices. You probably know what an electrical engineer is. They do the same thing. They take component pieces, they take resistors and transistors and inductors, and they put them together and they make electronics and electrical stuff. You can do this with every engineering discipline, and you kind of know what they are. You take components and you build stuff out of them. Well, in material science and engineering, like I said, we are builders. We're building solid matter. And so when I say that we build, what are my components that I build out of? And the answer is that the components are atoms and molecules. So in my field, we take atoms and molecules and we try to figure out the rules for how to put those guys together in unique and interesting ways in order to build solids. Now, there's an instant corollary of that. How do you push around atoms and molecules? How do you build out of those? You don't pick them up and put them together. You have to really understand basic science. You have to really understand physics and chemistry and mechanics and biology. Because to me, as a material scientist, these are tools. These are the tools in my kit from which I'm going to sculpt solid matter out of atoms. Let's talk about structure. I'm going to push around atoms, and I'm going to make interesting and unusual patterns of atoms and molecules. And that's the structure of a material. In fact, if there's one word that's most critical to material science, it's structure. It's about getting all the atoms in the right place, because what I want to do is evoke fascinating structures that give rise to interesting properties up at the upper level here. And if I can get interesting properties out of matter, then I can do things with it, right? I can make products, I can make devices, and I can serve the needs of society. So, are we an engineering discipline or a science? The answer is sort of both. We're the discipline that integrates across those. I take all the available tools of science, I use them to engineer solid matter, and I deliver products and devices to society. Now, that vertical integration, 50% science, 50% engineering, is something that we try to cultivate actively. We're trying very hard to do both of those things. And when we talk at the end about what that means for libraries, that's an important component. Do we look like an engineering department or a science one? Yes, we look like both. I also like that my discipline is really, how shall I say, it's sort of like agnostic or Catholic in terms of like what we care about. We care about everything. Like we care everywhere we want to engineer a solid. Like every single discipline touches ours, right? We serve every possible industry. I want my students to go out and become leaders in every industry, right? Whether it's healthcare, biologically oriented, or metals and engine coatings and all of that. We do it all. So, I'm going to start with a little demonstration. I'm going to need a brave volunteer. Or a not brave volunteer. Okay, it's all yours. Come on up. I'll pick you because you have like the maximum number of people to disrupt to get up here to the front. All right, so I'm interested in taking ordinary materials, restructuring their insides, and endowing them with unusual and magic properties. And this will be a little bit hard to see, but we'll pass it around when we're done. I'm holding in my hand two arches. These are wires of metal, and they're both kind of shaped in an arch. I don't know if we can see that or not. But these two are actually almost the same exact chemistry. If you cut them open and measure like how many atoms of each type there are in here, they're both mostly copper, they both have some aluminum, they both have some nickel. They're pretty close in terms of their composition. Their color's a little different, but compositionally they're almost the same. But the arrangement of the atoms is very, very different, and they have different properties. So this is sort of like a conventional brass. This is like all kinds of metals that you encounter every day. And if she takes this arch and she bends it, you know what's going to happen. Hold it up, bend it. What happens? It's deformed, right?
Because I'm super strong.
It bends, right? So it's not a surprise, metal bends. And by the way, when you deform a metal, what you're doing is, you bend that a little bit and it's flexible, right? It just flexes a little bit. Now you're stretching all the bonds in the metal. That flexing is stretching all the bonds. When it deforms permanently from arch to flat wire, that's because you're rearranging all the bonds. And there's all kinds of stuff going on in there where bonds are breaking and reforming and so on in order to change the shape. All right, now here is a specimen that we made at MIT. Hold that up and bend that puppy.
Straighten it?
Yep, straighten it out.
Oh, no.
Straighten it out, okay. All right, now like torture it. Wrap it around your finger. Oops.
Okay. Nope.
Yeah. We'll pass this around. I don't think you can put a kink in this thing. This is undeformable.
That's amazing.
And it feels different too, right? I'm going to pass this around. You're going to feel it. So one will be familiar, one will be not familiar. We call that a super elastic metal. And it's super elastic because that thing has been designed. The atoms are arranged in a certain way where when you start deforming that thing, at first the same thing in both wires happens, and that is you stretch the bonds a little bit. They all stretch. But at the point where the first one starts to break bonds and rearrange bonds, the second one actually undergoes a coordinated shuffle. All the atoms kind of move together in a military-type fashion, and they do a shuffle. And then when you let go, they shuffle back, and they're designed to do that. And so you actually get 10 times more elastic deflection out of that thing. And so you take a sort of a normal metal and you turn it into a super elastic metal. And I'll let you imagine what we can do with that, right? Like the imagination runs wild. So that's an example. That's what I want to do. I want to study the structure of matter. I want to use every tool in the toolkit of science and physics and chemistry and biology, push around those atoms, and get magic properties to pop out. And in my department, I want to do that with every kind of material. And so there's an entire spectrum that I'm trying to cover. I want to cover things that obviously I talked about this axis already. I want to work at the level of atoms and the theory and simulate and solve quantum equations and use electron microscopes and all that science nerd stuff. We want to do that. But in the end, it's about making products that improve people's lives. It's an engineering discipline, okay? And the other axis here now is the full spectrum of materials that surround us every day. They range from very, very soft things, such as the fabrics and polymers and even biomaterials. We are a material, are we not? This is solid. We want to be able to engineer at that soft end of the scale, and that, of course, interfaces with biology and medicine and so on. We also want to work in the middle here, EPM. I apologize for the acronym. Electronic, photonic, magnetic. This is the stuff of circuits, right, and smart materials that compute for us and do work for us. We want to be able to put every atom in the right place to make them do functional things. And speaking of functional and structural, at the very stiff end of the scale, I want to make rocket engines, and I want to make planes, and I want to make buildings, and I want to do all that. So what I'm going to do now, I'm going to go into show and tell mode. I'm going to give you a few examples, and all of these, by the way, are from my department at MIT. I actively, as a department head, try to cover this space, and the way we do that is by hiring faculty to make sure that we sort of do a little bit of everything. And I'm going to start on the soft end of the spectrum. So let's start with biology. This is your brain. And this is one of my faculty members, Polina Anakeva. And she studies how materials interface with the brain, or more generally, not just the brain, but neurons. So in the spinal cord and in other organs and so on, wherever there are neurons, she's interested in how are we going to interface biology with materials and electronic systems. Has anyone ever heard of deep brain stimulation? Does that sound familiar? Wow, you all know what that is. So would someone like to describe it to me, like in plain English, what it is? Yeah.
They go into the brain and disable a little piece of it, and if for a person who has Parkinson's with shaking, it usually will stop or reduce the shaking.
Exactly right. So this is a way that we treat Parkinson's, which is a neurological disorder, and the way in which they do it, you described it very well. I'm gonna put a little color on it, because basically the way I see it, they take a steel nail and they drive it into your brain, right? And that is pretty much literally what they do. They drive an electrode in through the back of your head into your brain. All right, so this was invented in the 1930s. A big steel nail was a cutting edge technology back then, I guess. But so is that the right way that materials are going to interface with the brain? No, I mean, this is sort of a rudimentary way that we interface with the brain. The brain is a complicated piece of matter, right? It's a functioning piece of matter. It has chemical and electronic function. And what Polina Anakeva does is she designs the materials that are going to go in there, and unlike just plugging in steel nails or steel electrodes, which can damage the tissue and cause a whole lot of problems, what she does is she is using all the tools of material science to make probes that are compatible with the brain. And when I say compatible, I mean compatible in every conceivable way. So first of all, she wants them to be very, very flexible. The brain is very soft, right? It's like essentially the modulus of Jell-O. So putting something really rigid in there, imagine putting a steel nail into Jell-O and now shake it a little bit. What's going to happen? It ain't pretty. But if you take a very flexible polymeric fiber and put it in there, now it can sort of go along for the ride on the jiggles, and it won't cause as much damage. So she wants to make probes that are extremely flexible. They're made out of plastic or polymer. They have to be biocompatible. Not just biocompatible, but compatible with the brain environment, which is unusual. And then simply putting in a piece of polymer into the brain doesn't do much for you. What you really want is to interface with the function of the brain. And so what she tries to do is make these fibers where if you zoom in to the nanoscale, they actually have a whole bunch of features in them, such as electrically conducting electrodes, right? So metal wires. In some cases, she likes to put in holes so that you can inject medicine down the center of this fiber and put it into the brain. In some cases, she would like to shine light into the brain so she can optically sort of trigger neurons to fire. So I'm going to pass around this piece of show and tell. Polina has done some amazing things making fibers, and this is a sample of 7 of her fibers. And each of these in cross-section is a circle, And you'll notice they're all about 100 microns or 200 microns in diameter. So you're going to get to feel these. And these are not much bigger than a human hair. They're all very flexible, so you can wrap them around your finger. And each of them has internal structure down to the micron and nanoscale. And if you look at these pictures of the cross-section, you'll see all different kinds of geometries. There's one here that has a whole bunch of different metal electrodes, so you could spark different neurons in different places. She's got the holes in there. She's got light guiding. These are really amazing pieces of engineering. You can imagine a doctor now hooking these up to a computer and interfacing with the human brain. And in fact, that is happening. So how does one make these things? Well, that's what this image here is showing you. What she does is she takes a trick from the way that we make optical fibers. So like for the telecom industry, how do you make fiber optics? Or if you ever go to like Disney World and the kids at the parade, they got those fiber optics lights that they wave around, right? Well, fiber optics, they guide light, they're flexible, those are exactly what she's trying to do, but it's more sophisticated than that. And she uses tricks from that industry to make these neural probes. So here's how she does it. She starts by making a big rod of material that is made in the image of that tiny little thing that she wants. So she makes a big old cross-section, as big as a $50. And in it, she manually sort of builds the structure that she wants, and she wants to now miniaturize that whole thing. So she builds a big preform, and then she has this very special furnace where she heats the thing up, and then she can draw it down. And you can see that I'm going to pass this around. So it starts gigantic, but she's worked out all the science and all the flow so that she can get this whole thing to sort of neck down and flow into this very fine fiber. And she can just draw these out and spool them up, cut them up, and send them out for surgeries and so on. So that is material science and engineering. Using everything we know about materials, combining all kinds of different materials together in new ways, manufacturing something, and interfacing with an industry. And in this case, directly plugging into your brain. So this woman will change the way you think, especially when she plugs into your brain, right? So while we're on biology, this is a device that interfaces with biology. As I mentioned before, biology is also matter, right? We are all made of matter. And the matter that biology makes is pretty amazing in a lot of ways. And in fact, cells are materials. A biological cell is a squishy little polymer ball, right? And so what if we take the materials viewpoint and start studying cells like they are materials, which they are. This is my colleague, Professor Van Vliet. And let me tell you what she's been doing. So here's a rat. This is an unlucky rat. This rat has been irradiated, okay? So, and far from coming out with superpowers, this rat is dead. So this rat has been irradiated, and it, in fact, has killed off its bone marrow, all right? Now, if you wanted to regrow bone marrow, if you wanted to, try to treat someone who's been irradiated and help them regrow something like bone marrow, how would you do that? Well, you might use so-called stem cells. Do we all know stem cells? Good, nodding and humming, I like that. All right, so stem cells are these magic cells where, you could harvest them from, a healthy rat, and you could, multiply them and grow them. You could think about injecting those in there, and they would regrow something like bone marrow. Very interesting idea. But here's the problem. When you go and you harvest a bunch of cells, those are all different from one another, and only some of them have the magic power to sort of regrow into bone marrow. So there's sort of this problem like, we've got quality control here. We've got all kinds of little polymer balls, which we call cells. Some of them are the ones we really want, which could treat this mouse and maybe save its life, and some of them are not. And so now, what can we do here? And what Professor Van Vliet has been working on is taking all the tools of like materials analysis and quality control and applying those to stem cells. So, incidentally, here's what happens if you try to inject stem cells into this rat. So I apologize for the cluttered graphic, but here's how you read this graphic. What you've got here is, this is the number of days after you irradiate the mouse, and if you don't do anything to this guy, you take a whole bunch of mice, say 100 of them, and now you wait. If you irradiate them, you watch as they all die within 2 weeks, right? So that's what this is. They're alive, now they're dead. Now, if you just take a bunch of stem cells or a bunch of cells that you've harvested and you hope that it's going to regrow marrow, you can inject those in there, and you hope it does something, and it kind of does, but the bad news is that they start dying at about the same point. They just kind of die more slowly, and it really doesn't take. So if we really want to make treatments out of this stuff, we've got to actually figure out which ones of these are working and which ones of these are not working. We have to, in short, go in and treat these like a materials production facility and do quality control. So Professor Van Vliet does things like this. She makes little devices that are designed to sort and measure cells. And this one is sort of an inertial sorting device where she pumps fluid through this spiral channel, and she gets these cells moving, and so when they shoot out this end, the heavy ones go over here and the light ones go over here, and she can sort them by size, okay? And then once she pulls them out by size, then she starts testing them like a material scientist would. She uses a little nano indenter, and she squishes these guys, and she figures out, what is their elastic property? Like, how big are they? How elastic are they? And actually, so their size, their elasticity, how much they fluctuate. She goes in and she measures these like she's on a production line, and she identifies the ones that work and the ones that don't work. And this is the result of that. If you end up picking the wrong ones, then mice die really fast. But if you're smart and you identify the ones that work and you use methods of sorting, then she can keep these mice alive, and she can keep them alive indefinitely and regrow bone marrow. So this is how materials science, treating biology like it's a material, is going to lead to new treatments and hopefully help us all. So those are two examples from the soft end of the spectrum. Now I'll show you a couple examples from the middle of the spectrum, where we talk about functional materials, electronic, photonic, magnetic. All right, here's a quiz. What's this? What's this thing? Does anyone recognize that? It's a vacuum tube, exactly. You don't look nearly the age to recognize a vacuum tube. I think we're all, this has not been a technology in a long time because we've replaced vacuum tubes with transistors, right? This is like the defining triumph of material science and engineering. Big, clunky device, complicated to make. It's a switch. It's an electronic switch. And when they figured out how to make the first solid-state transistor, a revolution happened, right? We took a clunky, complicated system and we turned it into a tiny piece of material. And you know what's happened as a result of that, right? So this is where the computer chip came from and miniaturization came from. And now these chips are so pervasive, you probably have like 5 of them on your person right now, right? Like this is what has made computing pervasive. And it's all because we replaced clunky system with a material innovation. And just look what that did to our world, right? Think of how powerful we are now because we have all this in our command. Now, I want that story in your head because the next one I'm going to tell you hasn't happened yet, but you're going to see this kind of story play again and again as solid-state materials replace complicated systems. And I'm going to tell you a story from another one of my faculty members. This is JJ Hu. And JJ is about to effect this same revolution that you just saw in computing. He's about to do that in the sensing of chemicals, okay? So think of all the places we'd like to measure chemistry. Wouldn't you like to know the air quality in here right now? Wouldn't you like to know, if the drinking water is safe in Mexico? There's a million places where you'd love to have chemical information. How do we measure that stuff now? Well, you take samples, you send them to a lab, and you measure them in some large system. And so here's an example. This is an infrared measurement system. If you work with chemistry departments, this is like bread and butter, right? Like to analyze a sample, you take it, you put it in this machine, you close the lid, it's as big as a bread box, and you get data out of it, one sample at a time. Just imagine what would happen if, again, think of that vacuum tube. This is to a vacuum tube as transistor is to whatever JJ is doing. So that's what JJ, in fact, has done. Just in the past year or so, JJ came up with the following material solution to this problem. He made films of material that are very carefully chosen, and it starts with silicon. So he sort of starts with the same wafer on which we make computer chips, right? He has to grow a ceramic layer. This is a semiconductor, by the way. Semiconductor insulating ceramic layer. On top of it, this is a complicated ceramic glass. This is a glass layer. This is a different glass layer here, and he works with the same types of devices they use to make computer chips, But what he did here is he made lines on top of a chip, and these lines can guide light, okay? So this machine here shoots light through the sample, and it measures the way all that light sort of refracts and interacts with the sample. What JJ did is he figured out how to put it on a chip. And what you're looking at down here, this is the transistor moment for chemical sensing. Because what you're looking at here, these are racetracks for light. These are called waveguides. So on a chip, he can now shoot light in on this side, and it will follow this curve. And so he can, instead of having to shoot it through space and through a vial of chemical sensing, he can shoot it around on a chip. The scale here is 200 micron. So again, that's like the same size as those fibers, right? Teeny tiny little things, barely visible. And he can actually build little pads on top of there. And now any chemical that touches this pad interacts with that light in the same way it would have over here. And so the amazing thing that he's done is he's shown that on a chip, he can reproduce what this bread box does, right? And so here it is. He's able to measure, here he's showing that in a beaker, he can measure both the amount of toluene and the amount of ethanol. And his data points here are right on top of the data points that you get out of this machine. The difference is, though, that this is so small you cannot see it, and it's on a chip. And just like all the computer chips, we can actually use the tools that JJ's come up with, and we can make thousands of them on one chip. So in the same way that first transistor led to all the phones and computers and all of the ubiquitous computing we do, I want you to now think about what the world looks like in a few years when now, with a wafer like this, with photonics integrated on it, that's what this is, we're going to have sensors everywhere. What happens when chemical sensors are everywhere and we know everything about the environment around us and our air quality and we don't need a smoke detector anymore. Your phone will know. So think about that. This is, in fact, this is from a different professor in my department, but this is the first wafer ever produced where it's a silicon chip, it's a computer chip with integrated photonics, and you can see how many little devices there are on there. So that's coming. So think about that. Wherever, from vacuum tube to solid state, that analogy is what material science does. We're going to do that in chemical sensing. We're going to do that in other domains as well. How about magnets? I'd like to talk about magnets. This is Professor Jeff Beach. He's in my department, and he is very interested in magnets. And I'm going to show you a little trick that Jeff has pulled in the past few years. What you're looking at here is a tiny little piece of a magnet. Again, notice the scale bar here. This is 200 microns, 250 microns. Again, similar size to those fibers I've been passing around. So on the cross-section of those fibers, you're looking at a magnet here, okay? And what Jeff has done is he's made this magnet in a film. It's a thin film. It's a little square film of magnet. And he has wired it up with electrodes. And what he has discovered is a way that he can control the magnetism in this film. And I'm going to show you this movie now. What you're looking at here in red, this is the magnetism. So in a magnet, there are two poles, right? So this is like the North Pole, or let's call this the South Pole. It's on the bottom. South Pole, North Pole. This magnet, all the poles are aligned, right? It's a single magnet. You're looking at the South Pole of this magnet. Now, watch what happens when we run his movie. He's figured out that on this film, once he applies voltage to the film, this magnet, solid sheet of magnet, when he turns on the voltage, look what he can do to it. He can flip the polarity of this magnet by pressing a button on his computer. He can sort of turn on and off the magnetism. Not only can he turn it on and off, he can pattern it. He can make a magnet pattern its magnetism. That's the MIT dome, if you don't recognize it. So he can tell a magnet where it's going to be north and where it's going to be south. In short, he can pipe spin around. We call it magnetic spin, right? Spin up, spin down. Oh, now he's getting cocky. He can turn it on and off really fast. Okay. Anyway, so here's what I want you to think about. Imagine a computer where, in a computer, in a circuit, what do? We run electricity through all these lines and all these switches and stuff. Imagine now, instead of running electricity through lines, we don't have to run anything physical. We just pipe the magnetic spin around. And that's what That's what we call spintronics. Have you heard the term spintronics? Spintronics is like what's after electronics. When you make a computer chip and you run a bunch of electricity through it, what happens? What happens if you turn on your computer and you run a bunch of electricity through it for a while? It gets hot. Yeah, because all those electrons, they have resistance. They flow through there and they heat up, and we have to get all that heat out. In this case, he's moving around the spin, but not moving around the electrons. He's just moving around the magnetism inside the sample, and he can drive it all with voltage. So it's very fast, it's very efficient, it doesn't create a bunch of heat. Spintronics is what replaces electronics, and this is the kind of thing that Jeff is working on. So that's material science. So you can see what we do, right? All the atoms in all the right places, manipulate the properties, do amazing things. Let's talk about functional, structural, those kinds of things. Fun fact. If you make 1 kilogram of steel, how do we make steel? Does anyone know? Where does steel come from? Yeah, steel is mostly iron. Where do we get iron from? Maybe that's the better question. Get it from the ground, get it from ore. Ore. What is ore? Rocks. It's rocks. It's not metal, right? In the case of iron, it's iron oxide. It's basically rust, right? So you dig up rocks and they contain iron oxide. It's oxidized iron. And the way we get iron is by deoxidizing it. And so the way you actually get iron is by, you got to get all this oxygen out of the rock. And the way we do that is actually by reacting it with carbon. So maybe you've heard of the term coking coal. We use coal. Coal plus iron ore. You mix those things together, and what do you produce? You produce steel. Yes, you produce a little bit of steel, but what else do you produce? Yes, exactly. So actually, a steel factory, for every kilogram of steel that one makes, one ends up making about 2 kilograms of CO2. So a steel factory, actually, it's really a CO2 factory, and steel is the byproduct, right? So now just think about that, right? So if we care about the environment and if we care about CO2 emissions, the way that we make materials has a huge impact on those things. Iron is a huge segment of CO2 emissions, and the other metals are not much better. To get metal out of rock, we put a lot of carbon dioxide into the air. And that's a big challenge for material science. Other environmental things are critically important in material science as well. Solar cells. What are those made of? Those are silicon. That's also material science. So those chips that we passed around, same basic material in a different form. The only way we're going to get new energy sources is by having materials that can harvest energy for us. Transportation, batteries. A huge fraction of my department studies the material science of batteries, because a battery is a complicated system of all these different parts that all talk to each other. Many of them are solid, and they interact with liquids, and it's highly corrosive, and so on. So that is a huge area for us. The other thing is the shell of this vehicle. It's been steel traditionally. So whenever we're driving around, whenever we're transporting things, we're moving around a whole lot of heavy weight, and that decreases our energy efficiency. In the future, we have to reduce the weight of that. And so we spend a lot of time trying to lightweight materials and make them stronger. Here's another show and tell piece that I'll give you. I got a couple on lightweighting. Lightweighting is very big business for material science. This thing here that I'll pass around is a material that you know well. You use it all the time. It's aluminum. But this happens to be a foam made out of aluminum. So this kind of looks like styrofoam, and it kind of feels like styrofoam, but it's aluminum. And so it has the strength of aluminum, but it's very low density. And in fact, as you add the holes to this sheet and you make it foamy, it gets lighter way faster than it gets weaker. And so actually you take a ton of weight out per unit strength. So this is a huge innovation for like aerospace and transportation. I got another one for you here too. Does anyone recognize this thing? It's a ball, yeah. Napkin. Yes. We spend a lot of time researching modern napkin rings in my department. Yeah, it's sort of like this is a ball valve. So you can imagine this like embedded in a pipe, and then I might turn a handle, and this thing would turn, and so there's an open and there's a closed, right? So this is a valve, and this is sort of emblematic of like a million engineering components that are in systems everywhere, right? On a rocket, there's a ton of valves. In aircraft, there's a ton of valves. this is usually a valve. It's a mechanical type of thing, right? Because it's going to wear. It's going to sit in this pipe, and we're going to turn it, and so we worry about it wearing and having a good seating. It also needs to do what? This is going to carry fluid of some kind, so what else are we worried about? Rust, corrosion. Worried about corrosion, absolutely. So this is a very typical valve, and it is made of stainless steel. And the stainless, of course, means that we're adding corrosion resistance to it. So here, hold that for me. How much does this weigh, Eugenia? Is that a pound or two? All right, so here is the MIT answer to that thing. This has the same strength as this thing. Yeah, we'll pass those around. This is the future, right? Things that we developed in the 40s and 50s that solved the problem the first time are not the way we're going to do it in the future. What happens when everything around you gets lighter by a factor of 3? When every piece of aluminum gets lightened to the weight of that styrofoam panel that we're passing around? When all the metals get lighter? Just think about what happens to your world when everything gets lighter. It's a pretty different world.
So the cars would be still as safe, but way less.
Exactly. That's exactly right. If we take the weight of a car down by 1/3 without making things weaker, then yes, safety remains constant, but energy savings goes through the roof. So the way we solve our energy problems, the way we solve our environmental problems is with material science. And that's the message here on the final piece. Another thing I'll mention, this is Professor Elsa Olivetti in my department, and what does she study? Recycling, yeah. It's not junk anymore, right? It's now an input material. So what Professor Olivetti does is she takes the field of industrial ecology and she marries it with materials science. She is, I think, one of the world's first materials industrial ecologists. And what she basically does is she studies the end of life of all of the products that we make out of all different kinds of materials. And she says, all right, how do we dig stuff out of the ground, now we make it into something, we use it, and then we throw it away. How do I close that loop? How do we close that loop so that instead of throwing things away, we're using more of it? And at every step in the process, how do we design to recycle? And what she's particularly interested in is, in the first place, before we design something, let's design it with recycling in mind. So this is the way material science is going to address these kinds of problems. All right, we talked about iron and we talked about steel. I want to share with you, what the future might look like if we do a good job on the material science. This is Professor Antoine Eleanor. Antoine is famous for having worked, he's at MIT now, but before he came to MIT, he worked at ArcelorMittal, which is the world's largest steel company. And he built this happy fellow right here. And what this thing is, it's the world's first reactor that takes iron ore, which, remember, it's iron and oxygen together, iron oxide. And he had developed a new process where what you do is you run current through this thing. So instead of putting coal into it and chemically reacting away the oxygen, you run electricity through it, and you actually bodily separate iron and oxygen. And so the emissions from this thing are iron and oxygen. So this is a steel production facility that, instead of putting out CO2, is literally CO2 free, and it puts out oxygen. Okay? So, and the way it works, it's almost magic. I don't think I even understand it. But what you do is you take rocks of iron oxide and you crumble them up into little pieces. So you're looking here at a tiny little sand pebble of iron oxide. It's going to be orange, right? It's a rust flake. And this is a slurry. And they figured out a chemistry where they can put all the rust flakes in there in these little particles. And when they start running current through this thing, they actually watch as these little particles, they convert. And you can see here there's a transformation front going across this thing. On one side it's metal, and on the other side it's rust. And so you just literally strip the oxygen out of this side, and eventually you convert the entire thing into a particle of iron, and the oxygen went off into the atmosphere. So that's amazing. Like, think blast furnace from the 40s, billowing smoke, belching CO2, and now think about room temperature reactor spitting out oxygen and iron. Like, this is what the future looks like when we do material science with the environment in mind. All right, on the structural side here as well is manufacturing. How do we make things? Well, I bet you all know what this is. It's a 3D printer. Yeah, we all know what this is. We didn't know this 5 years ago, right? But now my library has one, right? And like, I didn't mean my school library. I meant like my town library, right? There's children's books and 3D printer. And all the kids know how to use this thing, right? These things are pervasive. And so the way we make plastic is changing, and it's changing rapidly. And this is not happening just in the way we prototype and make little parts and baubles. It's changing the way industry makes plastic parts as well. That is a story of material science, right? It's a change in the way we make material. Let me tell you a personal story. This is my own story, is that, you know, I started noticing these things. My kids started noticing these things. And I saw that there was this big change in manufacturing coming in the way we make materials, 3D printing. And I said, all right, I'm a metallurgist. What I work with is metals. Why don't we print stuff out of metal? Can we print in metal? And the answer is, yeah, you kind of can. I started thinking about this in around 2011. And in 2011, let me tell you, it didn't look like this. It was not a $3,000 piece of equipment that you could buy and put in your local library. It was a major installation. It was, you know, from this wall to that wall, big piece of equipment involving lasers and electron beams, and very expensive, very elaborate. It would have cost $1 million at that time to buy one. You need an expert to run it. A lot of safety hazards. In short, the way we make metal and the way we make plastic look pretty different. And so I started thinking about, you know, how could we do this differently? And I worked with some collaborators, and we co-founded this company, Desktop Metal. And I want to just show you where I think the future is in the 3D printing of metal parts. So we came up with this little device here, which we call our Studio System Printer. And what you're looking at is essentially, this is a print head, and this is the stage. And so this thing can come over and print a little part here. And I'm going to show you a video of what that looks like. Now, how do you print metal? Well, metal is pretty strong. You're not going to be just like squeezing it, right? You don't squeeze metal like out of a test tube. You can't heat it up hot enough to do that, right? Like I'd have to have red heat if I wanted to squeeze metal here. Like I don't want red heat in my local library, right? So I can't do that. So what is a material science approach to do that? Well, what we came up with is we take metal powder and we mix it with plastic. We mix it with polymers. And so we end up with metal powder bound in a polymer carrier, and the whole thing is kind of like toothpaste now. And it prints just like the one at your local library. Let me show you that. Let's hope this movie plays. So here's Joe Engineer, and he's using software, and he's designing a metal part. This is a hinge. I have one of these here. I'll show it to you in a minute. He wants to print this in stainless steel. Now what he's going to do is he's going to design this thing, he's going to send it over to that printer, and it's going to print very much like a 3D printer plastic one. It's going to squirt out this bound metal, right? Metal powder in a plastic. And so here it comes. It's moving, it's drawing. You can see that it's drawing these layers. But now it's not metal. It's metal in a plastic, right? Not good enough, not good enough. So this is still a gooey plastic, but it's got a bunch of metal in it. So what is he going to do? Well, the way you get metal powder and turn it into solid metal is you fire it. And so we have a furnace. So after you print it, you put it into this furnace, which is a self-contained thing, and it fires it to high temperature. When you go to high temperature, you burn off all the plastic and polymer, and you recapture it. But the metal consolidates and shrinks, and you get a solid metal part. So I'm going to pass this around. But I got to show you one other thing. So now we can print metal parts. This is coming. I got one other little trick I want to show you. So here's this part. The part I want is that one that we just saw him with. I just want the hinge. But in order to get there, we printed a solid base. And we didn't want this thing to slump and deform when we put it in the kiln, right? So we drew in all these other supports and so on. So you kind of draw this thing with a bunch of extra stuff attached to it. And in the end, I don't want all that stuff. I want to be able to detach this thing, right? So let's see if I'm smart enough to do it. So this thing, I want it to come off, and I want all this stuff to sort of be recycled, right? What I really want is this part here. And so the question we asked ourselves is, okay, how are we going to do that? How are we going to print all these supports? But I don't really want to have to go like cut it and machine it or chemically etch it. I want this to be user-friendly so that my kid can do it, right? So how do we do that? I'll pass that around, by the way. And so what we came up with, and again, this is a material science question, is how do I make something that I can fire it and I can sinter it and I can turn it into a solid chunk of metal, but then I can detach it. And what we came up with is not only do we have a head on here that prints out the metal, we have a second head and it prints out a second material. And so everywhere there's an interface, so on this base and on all these supports and all these like infill regions, wherever I want the metal to not be part of the structure, I use this second head and I print a special interface layer, and that layer is designed to do exactly the opposite of what the metal does. Instead of consolidating and turning into solid metal, it actually turns into dust. It turns into sand. So when you heat the thing up in the furnace, the metal consolidates, the interfaces turn into dust, and when the thing comes out of the furnace, Joe Engineer can come in here with his screwdriver, and he can just pop out these things here. So all the little infill regions. These are solid metal, by the way. They did consolidate, but they detach from the part, and now he can just manually sort of rip it off. And that part that I'm passing around, you can see it's now detached from that part. So now you really can. You can print a metal part, anything you can imagine. You draw it up in the computer, you print it, and you've got it in front of you. So material science is about making materials. That piece of metal in your hand, that's just 316 stainless steel. That's a common stainless steel, but we're making it in a pretty different way. And so that, I think, can impact the industry. In the future, I'm hoping that this kind of printing, you marry it now with new materials. And so I'm showing you here, this is actually a 3D printed part made of what I think is the strongest metal ever produced. So this is an MIT alloy. It's based on the metal tungsten. And I don't know how many of you feel like you need a metal Carmex jar, but if you need a really strong metal Carmex jar, I guess we've got one for you. There it is. But we might make things like tools and so on out of these extremely strong materials. So now not only is it a new way to make them, but it's actually a new material with improved properties as well. All right, that is material science and engineering. So in every domain, from the very hard, from structural, boring components like pipes and hinges and stuff, to active materials, electronics, magnetics, all the way to biology, you can see what we do in this field. We're trying to put all the atoms in exactly the right place and impact every possible industry. I thought I would throw in just a few words here on curriculum, because I come from an academic department. And I care a lot about training the next generation of engineers and scientists who will go out and do this kind of work. In my department, there are roughly 400 or 500 people. We are mostly a graduate operation at MIT, but we have a strong contingent of undergraduates as well. And I told you at the beginning that I care a lot about balancing basic science and engineering. And I really do. If you go and you look at what an engineering department looks like and what a science department looks like, they're pretty different, actually. So an engineering department, for example, chemical engineering or a school of engineering, will often produce students that go out into industry, right? So here we have postdocs and working. So this is graduates who leave a materials science program or leave an engineering program. 2/3 of them are going out directly into industry. The other 1/3, apparently postdocs don't work. That's bad news. I got to go yell at them. That doesn't sound right. But anyway, so the graduates of our program, in engineering, they mostly go to industry, and some of them sort of stay in the academy. And in science, it's sort of the opposite. In science, we produce a lot of people for the academy, but not a lot for the industry, right? And so that's sort of the dichotomy between engineering and science. And what I try to do in my department, in material science and engineering, is I try to do something like this, right? Our department cares about both equally. We want to serve industry, we want to serve the academy. We're an equal blend of science and engineering. So that's something unique about material science. I'll also just mention in passing that this is an extremely innovative field. You can see we make devices, right? We make products. We change the way industry works. And so if you look at all of the different people who invent stuff at MIT, including, incidentally, our provost is on here. I got to go talk to him. I've been meaning to ask him about this. That's unusual, but I like it. But anyway, material science and engineering is one of the most innovative patent-producing, license-producing, startup-producing centers at MIT. So this is a very innovative and entrepreneurial discipline to be in. We're second only to electrical engineering and computer science, and incidentally, not to brag, but this department is like 4 times our size. So this is like 120 faculty doing a really nice job, and this is 35 faculty just killing it. The other thing I'll mention is that materials science and engineering it's central to every discipline. Someone mentioned that earlier when I asked what is this field. We take all sciences in as tools, but we connect to every possible type of engineering. We're very central. And at MIT, this is like explicitly true. The number one priority on our campus right now, we're opening the doors on a brand new materials research building right now as we speak. This summer, this building is being commissioned and opened, and it is literally right at the heart of MIT next to our Great Dome. It is a $400 million investment in a research facility basically for materials research. So this is a very important thing in a real sense across our entire institute. In terms of curriculum in material science and engineering, so this is a map of MIT, and I apologize, don't worry about the colors here. This is, again, the patents. I just want to show, we're so good at patenting. But anyway, the center of MIT is the dome. It's right here. That new building is right here. My department is all around the center of MIT. And one thing I want to say about the curriculum of material science and engineering is that our curriculum is extremely laboratory-centric. And I'm not sure this is normal all over the world, but at MIT at least, when you join a material science and engineering department, the first class you take is in the lab. And so our entire footprint here is built around highly visible laboratories, and the curriculum is laboratory-centric. When you take a lecture course, it's married to a lab course, and it reinforces hands-on learning. So all this stuff I'm passing around, that's because my field is tactile. Like, we're very much about hands-on education. It's a very high-touch kind of curriculum. And the students are in lab literally every semester they're in the department. From the first semester as sophomores, they're in lab every single semester until they're out of there. And by the way, the final project in our department is a prototyping project. They work in teams and they have to make a product that is a material solution to a market need. Since I've talked too long, which is something I tend to do, I will briefly mention to you that one of the things I'm very excited about in curriculum at MIT, and I think this bears on your work as librarians, is that more and more textbooks are being replaced with flipped classrooms that use online courses. And in our department, we have plugged in very heavily to MIT's online university. MIT launched this online university, edX, in 2011. And I'm delighted to report that in the intervening 6 or 7 years, we have now essentially put an entire material science and engineering core curriculum online for free. So we are really delighted to have this as a tool for our own students. We do a lot of flipped classroom work at MIT, where our faculty, once they put their course online and their lectures are perfected and canned, and there are homework problems online and discussion forums, we let the students absorb all that, and then we spend more time on Socratic discussion and laboratory work. And I think this is the future of education in my field, that increasingly content delivery one-to-many, like we're doing right now, this is going to be replaced by watch the video first, now we do Socratic discussion and laboratory work. We're doing more and more of that as the years go by. If you're interested in this, the largest materials science and engineering course in human history is 3091X. We've taught this to over 100,000 students from around the world at this point. We've been running it for the past 5 years, and it's Introduction to Material Science and Engineering. Sign up for it, take it, enjoy it, it's free. We have a whole bunch of other courses, mechanical behavior, electronic materials, whatever you're interested in, we have the entire core on there. And again, I view this as the future of textbooks, right? This is an interactive textbook. All the lectures on there are actually, as you watch the lecture, you see the words appear on the right-hand side. It's searchable, so if a student missed a concept, they can search and find where was that concept talked about, and then It's all indexed to the lecture. It's quite amazing. And at this moment, incidentally, if you go back to where you guys work, if you're at a university, I am very interested right now in using this as a way to proliferate our field. I've put all these courses online to tell people what material science and engineering is. I'm trying to get the word out about what the field is. I'm looking for university partners who maybe they don't have a material science and engineering department. Maybe they'd like to field a minor in material science and engineering, but they wouldn't have the bandwidth to do it. Well, I've got all these classes that are online and fully graded and validated, and I would love to work with people to find ways to inject that into curriculum elsewhere. All right, I was asked to talk for like 2 minutes about what I use at the library, and so I'll just very quickly say that material science and engineering, we do use the library. It's very important to us. We have a material science librarian in our department, and part of it is that this is a field that is on the ragged edge of science. This is not like, just, doing engineering work and making prototypes. No, we publish, we invent, we study atoms, we study molecules. This is a ragged edge scientific field. The primary archival journals are critical to the field. I would also say that open access is something that we increasingly care about. And one thing that our library does for us, which I thought I would just mention because we think they're awesome for this, is that we have an open access policy at MIT where every article that we publish, MIT makes it free to the world, right? So the final typeset article is copyrighted by the journal, but the untypesetted article is made free by MIT to the world. And this is a huge thing for us. This is my own personal stats for the past few years. My articles, I love looking and seeing how they're downloaded 10,000 times to people who might not be able to afford them if they needed a subscription, right? Especially in places like China. My biggest audience is in China. That's a commentary on the Times, by the way. So those things are very important to us. The other thing I'll say is that we are engineers, and engineers live on data. And my students use the library because it is a data repository. So handbook type information, increasingly we're asking our library to subscribe to online data warehouses and thermodynamic databases and software that computes things that is fed by scientific data. This is critically important for us to do engineering work. Because we're engineers and we're innovative, we also care a lot about patents, and sort of having access to the patent literature is very important. And this last one I throw in here because I think many people don't appreciate that to be a good engineer, you've got to speak business a little bit, right? You got to know enough about markets to be dangerous. And so actually our students spend a lot of time thinking about, is this relevant to a market? And in order to do that, one needs business-oriented market studies. And so our students actually use the business library a lot. Okay, I'm done. It says end of slideshow. Thank you. I talked too long, but if anyone has a question, I'm happy to take it.
So, you talked the perfect amount, and we do have Q&A at the end.
Okay, great.
Okay.
Then I will talk to you at the end.
Coffee break upstairs, 15 minutes back here at 2:45.